Hello everyone. So in this video we will start by recalling what the definition of the derivative of a function is and see how we can understand the derivative as a function itself. Okay, so let's get started. So recall that the derivative of a function f of x at a point x equals to a is given by f prime of a, which is the limit as h goes to 0 of the difference quotient f at a plus h minus f of a divided by h. Now we can write the exact same limit as the limit as x goes to a of f of x minus f of a divided by x minus a. These two definitions here are actually exactly the same. Okay, now there's two important things to note. First is that the derivative at a point a is only well defined if the limit exists. Now this is important because we will see later cases where at certain points the limit does not exist, in which case the derivative is not well defined. Second thing to note here is that the derivative has a very nice geometric interpretation. Okay, so let's see how that goes in an example, which is the easiest way to see it. So let's choose a function. Say I choose a function being equal to x squared. Now I can graph my function, so graph f of x as a function of x, and what I get is something like this. So what this graph here is a graph of the function f of x as a function of x. Okay, now what does the derivative mean in this setup? Well, let's choose a point x equals to a, then there's a corresponding point here, a f of a, and what the derivative does is give me the slope of the tangent line at this point. So f prime of a gives me the slope of this tangent line here. But now one could ask, is there anything special about a? Well, of course, a is not special. I could choose a different point, say b here, with its corresponding b and f of b, and the derivative would give me the slope of the tangent line at this point, right? And I could do that for any point on my curve here. So in fact, using this, I can generalize the definition of the derivative as a tiny bit. So I'm going to write a new definition of the derivative as f prime of x being equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So really I haven't done very much, right? All I've done is replace a by h. But fundamentally this is quite different because now I can understand my derivative here, f prime of x, as a function. So f prime of x is a function itself. It is well defined for any x here in the range, in the domain of my function. So, well, in fact, we'll see some subtleties about that. But generally speaking, f prime of x is a function. So I've gone from a function f of x to a new function f prime of x, which is the derivative of f of x. So let's see how that goes in our previous example. So I chose my function f of x as being the square function, and I had the following graph for my function here. Well, I can look at the derivative at arbitrary points. For example, here I'll get the slope of this tangent line. Here I would get the slope of the tangent line here, and slope of the tangent line here, and so on. And if I put these slopes all together, I'll get a new function, which in this case will just have the following form. So this will be a new function, which is in fact the graph of the function f prime of x as a function of x. In this case, it turns out that f prime of x will just be the function 2 times x. So you see it makes sense. At x equals to 0, the function is 0, which is correct because the slope of the tangent line is 0. For any positive x, the slope here is going to be positive, which is what happens. And any negative x, the slope here is going to be negative. Okay, so let's do another example in some detail. So let's choose a very simple function and see how the derivative goes geometrically, both geometrically and from the definition. So let's choose the function f of x is equal to x. Okay, so what does this function look like? Well, again, I can graph my function. I'll get something like that. So this is the function f of x as a function of x. What about the derivative here? Well, if I choose an arbitrary point here and the corresponding point on the curve, well, the derivative turns out, the tangent line turns out to just be exactly the same as the line itself, right? And that's true for any point on my graph. Okay, so what is the slope of this line? Well, we see that the line is just given by f of x is equal to x, so the slope is 1. So from this point of view, I deduce right away that the derivative for any x should just give me the slope of the tangent line, which is always 1. So this is what I should get from the definition. So let's calculate that. Well, f prime of x is equal to the limit as h goes to 0 of f x plus h minus f of x divided by h. So I can replace the function here by the function we've chosen, which is just x. So I get the limit as h goes to 0 of x plus h minus x divided by h. Now you see that the 2x cancel. So I get the limit as h goes to 0 of h over h. Here I can just, h over h is just 1, right? H is not exactly equal to 0 because I'm taking a limit, so I can just do that without trouble. Get the limit as h goes to 0 of 1, which is indeed just 1. So the result is that my derivative function is just 1, exactly like we could see from the geometric picture. So that all makes sense. That's great. Now in the next video, we'll see many more examples of functions where we will compute the derivative from the definition and see that it is consistent with the geometric picture.